This video is about common and natural logarithms. So now that we've been dealing with logarithms and understanding their definitions, we're going to look at these two specific special cases. The common logarithm is a logarithm with base 10, and it's denoted by omitting the base number in the notation. So we're used to writing logs with little subscript bases by now, but log base 10 is abbreviated as simply log with no actual base written there. So since it's just omitted, we understand it, no matter what, every time it's gone, to mean log base 10. That's just an abbreviation. Similarly, there's a natural log where you have log base e, but if the base is written rather instead of log base e as ln, but ln will stand for natural logarithms. So these are just abbreviations we're going to get used to because these are very commonly used logarithms. Let's note a couple key things. First of all, graphing calculators have buttons devoted for the common log and natural log. That's a good thing. That'll make our lives a lot easier when we're trying to type in and compute some values. And secondly, graphing common and natural logs follows all the notes from graphing logarithmic functions with the respective base values defined. Okay, so this word might have gotten cut off there. That's the word base. So as long as we understand that the base values, which in our original definition of logarithms was, I think, a letter A, now those base values are different. So when you see ln of x, remember that's base e. And when you just see log of x, that's base 10. So those two abbreviations are what we're going to depend on for these definitions. Otherwise, everything works the same. So we understand what their bases are, and yet how we'll be seeing them when we encounter them in problems. Let's look at an example where we want to find the domain of the function. This time our function is given as f of x equals natural log. Notice it's just written as ln, but we know now that means log base e. So natural log of x minus x squared, all as the input in parentheses. Now we have to go way back to our definitions of logs. Remember, this actually means log base e of x minus x squared. When you see the ln, we now know that means log base e, which is just in line with all the other log definitions we started with, where we said that the input, in this case it's x minus x squared, that has to be greater than 0. Now that will help us find our domain because that actually defines it. So we need to say now that x minus x squared has to be greater than 0. Well, that's just a polynomial or nonlinear inequality, and we've done those in the past as well. Now we're getting to see why we might need those skills. So we're going to solve that with the spit method. That'll involve us writing this as an equation. So we'll say x minus x squared equals 0. And to solve this thing, this is factorable. If we take out an x, we'll have 1 minus x. So x times 1 minus x equals 0. This would tell us that x could be 0 or x could be 1. And in those cases, remember, we take the next step is to plot our solutions. That's P for plot. On the number line, we'll put them in order, so 0 and 1. And then we have to test around them. We're going to test this original inequality, and we could utilize a calculator to help us speed this up a little bit. For our second example, let's find the domain of the following function. It reads as f of x equals the square root of x minus 2 minus log base 5 of 10 minus x. So let's consider a couple pieces to this function, and we're going to have to treat them separately. The first piece was the root, and as we've seen in the past, that means what's underneath the root cannot be negative. So we should say that x minus 2 has to be greater than or equal to 0 in order for that piece of the function to be defined. But then for the logarithm piece, as we've been understanding here, the input for the log, which in this case is 10 minus x, that has to be strictly greater than 0 given the definition of log functions. So really where both of these are true is what we want to find. So let's go ahead and do a little more algebra. The first condition, where x minus 2 is greater than or equal to 0, if we solve for x by adding 2 to both sides, would say x is greater than or equal to 2. The second condition, if I were to get x alone here, I could do that by just adding x to both sides. I would end up with 10 is greater than x. And I want to find out exactly where they're both true. Sometimes it's helpful to look at a number line and put both of our boundaries on it. So we have 2 and 10. The first condition, where x has to be greater than or equal to 2, would be a bracket on 2 and then a graph going to the right. The second condition, where x is less than 10, would be a parenthesis on 10 and then an arrow going to the left. Now, we have to put the summary of this together to get one final domain, which means we want to know where they overlap. And you can tell that including their boundary symbols, we have a bracket on 2, and they both overlap in between these boundaries. So we'll say 2 with a bracket, comma, 10 with a parenthesis, and that will represent the overall domain of this function. For our next example, we want to evaluate the following expressions correct to 4 decimal places. The first example reads log. Now notice, when it says log, there is no base written as a subscript of log. If you go back to our definitions, that means it's automatically base 10, just because, again, nothing's written there, and that's what we assume with that notation. So really, this is log base 10 of 3 times the square root of 2. Now, that's fine to understand, but really we're going to do this in a calculator anyway. So let's go ahead and open up our TI graphing calculator, turn it on, and then find the log button down the left side of our buttons here. There's a button that says just capital L-O-G. That's it. That's log. And notice there's no base written with it, which means we assume it's log base 10, just like this notation we've been discussing. So we want log of 3 root 2, and we'll just type in the 3 root 2 as we're used to using our calculator keys here. Now, when you only have a singular number as an input for a log function, in the calculator, sometimes you can get away without closing the parentheses that were opened automatically for the log function. I recommend, though, getting in the habit of closing up parentheses, just for the sake of safety, and when problems get more complicated, it's essential. So we're going to close the parentheses around the 3 root 2, hit enter, and let the calculator do the heavy lifting for us. Now this problem wanted the decimal rounded accurately to 4 decimal places. So since the result reads 0.6276362526, and then it just cuts it off because of too many digits here. To round it to 4 decimal places, we'd have 0.6276. Lastly, let's do an example where we want to graph the function by identifying and graphing the parent function using a dashed curve, and then using transformations to graph the function with a solid curve. Now this is a familiar process to us by now. We will also want to state the domain and range. The function given is f of x equals 1 plus ln of negative x. Alright, so let's go ahead and identify a couple of key things. First of all, the parent function of this. You could recognize by the structure of this function, if you take away the bells and whistles, which would include the 1 and the negative in front of the x, if you eliminate those, then this is really just y equals ln of x, which again is log base e, or just natural log. So if that's our parent function, we want to do a basic setup with that one with a dashed curve, and then we'll go ahead and transform it using the given transformations. Let's take note quickly that the transformations would involve this 1 that's being added in the beginning. Remember, that 1 is added. It could be at the beginning or the end. That's going to mean we're going to go up 1. And then this negative sign that's in front of the x inside the parentheses means we're going to do a horizontal reflection. And that's all based on our understanding of transformations as applied now to logarithmic functions. Now, as we've done before with an example like this, when you want to do a parent function that's a log function, it's actually easier to think in terms of exponentials. That's just what we're used to in math. So we're going to rewrite this in exponential form. Now remember, this is ln is log base e, so let me just rewrite it that way again. We have y equals log base e of x. By the way, the parentheses surrounding the x, if x is the only input value, there's no like double terms being added or subtracted or anything, then you can actually drop the parentheses. You might see it as just log base e of x without the parentheses. It means the same thing. Now, to convert this to exponential form, remember we start with the base, which is e. So we'll say e to the power of y equals x. And those are equivalent forms by the definition of logarithm. We're going to go ahead and make an xy table to graph our parent function, which is this y equals log base e of x. We want to graph it though using the exponential form of it because it's just easier to work with. Meaning, like let's pick values for y that we just plug in as the exponent. When y is 0, e to the 0 is 1. So that's a nice easy point. Or when y is 1, then e to the 1 is e. Now remember, e is kind of a nasty number, but we can approximate it well enough for our graph, and we'll do that. Now let's get this parent function on our graph first and utilize the points we just computed in exponential form. So we have the point 1, 0, and we have the point e, comma 1. Now remember, e is 2.71828, so we'll estimate 2.7 down on the x-axis, and then we'll go up 1 for an approximate value for this point. Let's also recall that the parent function for log graphs have vertical asymptotes right on the y-axis. I'm going to throw one dashed in blue for now. We'll change it when we do the final graph here. But that's the case. Now we're also let's graph this full parent function by using a dashed curve following the shape of a log graph, which plummets downward toward the vertical asymptote, but then to the right increases, though kind of leveling off as it does. Now, this is the parent function. Let's also recall our transformations, which include up 1 and a horizontal reflection. Now, moving a vertical asymptote up 1 is actually invisible, as we said in our notes, which means our final function is going to have a vertical asymptote right on the y-axis as well. So I'm going to put like a red vertical asymptote over the blue one, meaning the red one is the final one. But then let's think carefully about the reflecting here. To reflect horizontally means we're going to flip this graph around the y-axis, which means the point 1, 0, when flipped around, will end at negative 1, 0. And the point 2.71828, right, the point e, comma 1 that we graphed, will flip at negative e, comma 1. We're seeing the symmetry there. Now let's not forget that we still have to, after reflecting these 2 points as we just did, shift our graph up 1. So I'm just going to drag the new points. I'll put the new ones in orange, up 1. So, okay, our vertical asymptote didn't change because we simply went up. If we had gone left or right, then we would have seen the vertical asymptote move. But now we're just going to draw a reflected graph that will resemble the shape of the parent, so it chases negative infinity down with the asymptote, but then it's going to rise and then utilize the 2 points we plotted as it trails kind of leftward, still increasing, but seemingly leveling off as it goes. And so this orange graph is now our final graph. We'll finish by deciding the domain and range of this function. You'll recall that domain is affected by the vertical asymptote, and so notice the final orange graph here. It's going left forever, so our domain will be negative infinity, comma, and then it goes no further than this vertical asymptote. So it goes up to 0, but not including it. So we put a parenthesis on 0. The range up and down, we use everything, so we'll say negative infinity to positive infinity. And you can refer back to the definitions of exponential and log functions and their graphs if you want to clarify that that indeed is consistent with those.